Adesso faccio l'operazione difficile. Hi.
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 Nice to have you here.
Nice to meet you. How are you doing?
I hope my microphone is working.
I can hear you well. Can you hear me?
Yes. Paola, you too?
Okay. Now mic should work.
I can hear you now.
Yeah, that's okay.
I also see you twice.
Yes.
Yeah. Sometimes twice. I'm very happy you accepted our invitation.
Oh, I'm glad you invited me.
So
I attended a few lectures and they were very nice. I couldn't attend the whole program, but it was very interesting.
yes, we had Rob and Frank on Monday, and it was nice. Unfortunately, Mark van der Laan couldn't present his work. But anyway.
He sent one of his students.
Yeah.
Yeah. I logged into I had set an alarm to log into when this person started presenting, but then I was a few minutes late and I couldn't follow the presentation anymore. So I thought
we have recordings.
Yeah, I emailed, and yeah, if the link is available, I would be very happy to have a look.
Yes, I think Corrado, do you know when recording would be available? Corrado is not.
Could I try to share my screen already?
Good morning to everybody. I'm intervening because Mrs. Wynants asked us to see the link, and she wrote me, and I told her that as soon as the link is available, we'll send it to her, of course. Okay.
Yeah, great. Thanks.
Got it.
Great.
Bye. Have a nice afternoon.
Thank you.
Thank you.
Could I try to share my screen?
Yeah, sure.
Test it. Okay. You should see my presentation.
Great.
Like a laser pointer.
Yeah.
Yes.
Okay.
Everything working.
Good to know that.
We are still in 5 minutes.
So who is starting the presentation?
Veronica is starting.
And I'm at 3 o'clock, right? Yeah.
Yeah, she will introduce the topic. Then there will be Danila. He is an assistant professor here in Italy, the University of Ferrara near Padova. And then it's your stage. And the last speaker is Ilaria. Dorigatti, who is working Imperial College, but she will connect later.
Is it an all-female session?
Yeah, yeah.
Oh.
Nice. It was our dream.
Sorry?
It was our dream to have just a female scientist session. So we. I'm trying to share the program of the day just for the audience.
Oh, hi.
Hi.
Oh,
Hi.
Hi,
good afternoon.
okay. I don't see if we have already participants. Hi, Annalisa.
Ciao Paola.
Thank
Buon
you for
pomeriggio.
grazie.
Buongiorno.
Thank you for joining.
My pleasure. When it's an interesting afternoon as this one, it's important to listen. You have still the yesterday program.
Yeah, this one.
Okay, great.
Okay, I think we are.
Paola, prima di, siccome poi io non riuscirò a stare fino alle 5 perché ho un altro meeting, approfittavo per salutare i ragazzi oggi che è l'ultimo giorno, non potendolo fare alla fine, ma proprio saluto. Io aspetterei ancora qualche minuto che...
Ok, allora aspettiamo ancora 5 minuti e poi ti do la parola.
Grazie. Abbiamo avuto quasi un centinaio e anche più di partecipanti nelle varie giornate, quindi direi proprio c'è stato un grande interesse per gli argomenti che sono stati proposti, direi bene.
Perfetto. E purtroppo ieri non sono riuscita a esserci perché avevo lezione.
Ma era una seduta molto logically oriented, ma molto interessante.
Poi seguo la registrazione.
Sì, sì.
Okay, I think that we would wait just a few minutes so participants can join.
We have already connected from Maastricht.
Yes.
Thank you for joining anyway.
Thank you for the invitation.
And also, I don't know if Ilaria, Dorigatti.
Ilaria wrote me, and she will connect later because he has another meeting.
Two meetings.
Meantime, I'm seeing that participants are enjoying, so we can just wait for a few minutes again.
Mm-hmm.
Already quite a good number for Friday afternoon.
Yeah.
You're right.
We have to raise a bit more the bar. Ciao Dolores.
Dolores, sei sola oggi?
Buongiorno, no, sono qua, che gironzolano, non mi lasciano in pace. Insomma, io mi scuso, ma alle 2:30 devo staccarmi perché ho 5 ore di lezione a scienze riabilitative, quindi Paola, scusami.
No, figurati. Always quarantine.
Abbiamo il tampone di uscita delle bambine sabato prossimo. Il nostro martedì.
Good.
Delirio.
But we are
Vabbè.
all fine.
Sì.
Okay, we have reached 60 people.
Nice number.
Yeah. For a sunny Friday is okay.
Not so sunny, depends.
Well, here it's very gray, cold.
Annalisa, do you think we can wait?
Yeah, I think we can start, not to be late. And I'd like just to thank all the people involved in this winter school. And it has been the first experience, and we hope to repropose this activity also next year. We had also the chance to with all the presentations, so maybe later on we will be able to put on Moodle or on the web some of the contribution. I think it has been very challenging, especially for PhD students and not really statistician or mathematician or engineer, but I think it has been really a broad overview of the problem of artificial intelligence in the biological field. So my gratitude to Professor Gregori and all the staff and the group of the biomedical and biostatistic and clinical epidemiology of our PhD course. And I would like to ask all the participants to contribute to the evaluation of this week, because we can, thanks to your comments, maybe we can improve or modify the program for next year. So thank you, and I will leave the podium to Paola for the introduction and the presentation of the afternoon.
Thank you, Annalisa. Thank you for being in the organization of this winter school, and welcome to everyone. Today is the last day of this successful winter school, and I hope all the participants found a lot to learn and also new insights. I can say that we had outstanding speakers in the last days, and I guess it will be the same today, because we have a really nice talk and great speakers. So today we are going to talk about machine learning and COVID-19. So it's a really interesting topic. And just to be in time, let me give the stage to Veronica Sciannameo. Veronica is a postdoc in biostatistics at the University of Torino. She's working with me, and she involved on a few projects about machine learning and COVID-19. So we have asked her to give a short topic introduction, and so please, Veronica, you can start and share your screen.
Thank you. Okay, can you see my screen and can you hear me?
Yeah.
Okay, thank you. So good afternoon, everybody. And thanks, Paola, for the introduction, and thanks to all the organizers for inviting me to present at this topic introduction. So we will talk about machine learning and prediction in COVID-19 epidemics. And as all of you know, COVID-19 is a disease caused by SARS-CoV-2 virus. And it is a global scale pandemic infectious disease, which emerged in November 2019 in Wuhan, in the province of Hubei in China. And this was the beginning of a major public health emergency. And then on the 29th January 2020, the first 2 cases were registered also in Italy. And globally, today, there have been more than 300 million confirmed cases of COVID-19 in the world, including more than 5.5 million deaths reported to the World Health Organization. In the last 2 years, many prediction models have been constructed with different aims. For example, many researchers were interested in the prediction of the epidemic growth, many others on the prediction of prognosis and diagnosis of COVID-19 disease. More in detail, we could be interested in the peak identification or in the estimation of RT and R0, or in the forecasting of new cases and new hospital admission due to COVID-19. And all these predictions could be helpful for example, for the healthcare authorities in the implementation of control and prevention measures. And furthermore, many prediction models have been constructed to predict individuals who will progress to more severe complications to deliver to appropriate and prompt therapies, which could have a significant impact on the patient's outcomes. And finally, many models have been also developed to predict diagnosis, for example, to differentiate COVID from non-COVID patients and to optimize the screening of patients with severe disease to minimize mortality and hospital admissions. Lots of different models have been proposed to predict in general epidemic growth, also for other diseases like SARS, Ebola, and in particular in the last 2 years for the prediction of COVID-19 epidemic growth, but yielding sometimes also conflicting results. For example, many researchers have chosen to describe the epidemic through stochastic models like compartmental mathematical models, I mean SIR, SAIR, SAIRD, and so on. And many other researchers choose the more classical statistical models, like, for example, the exponential model, logistic, Poisson, ARIMA, and many others choose more advanced machine learning and deep learning approaches, like super vector machine, random forest, k-nearest neighbor, long short-term memory, convolutional neural network, and the convolutional LSTM, which is a mixture of the previous two. Deepening slightly, we can say that a compartmental model assumes that the overall population is divided into compartments like susceptible individuals, exposed ones, infectious, recovered, or dead. And compartmental models are a mathematical approach to model the infectious diseases. And differential equations are used to reflect the dynamics of the infectious diseases, describing the relationship between the rate of change at fixed time of the number of individuals in different population compartments. And such kind of models can predict things like how a disease spreads, the total number of infected, or the duration of an epidemic. And such models can show how different public health interventions, for example, may affect the outcome of an epidemic. Then, on the other side, we have phenomenological models which have the advantage of allowing simple calibrations to the empirical data collected, and the most used for COVID were the logistic growth model, the generalized logistic growth model, Poisson, and in many other studies, ARIMA was used, which is a model which includes autoregressive integrated moving average models, and often it requires stationary time series, which often was not the case of SARS-CoV-2 time series, but with some transformation of data, we can easily apply this method. And furthermore, many also advanced machine learning methods have been applied in the context of COVID-19 epidemics to forecast the epidemic growth, but also for diagnosis and prognosis predictions. A strength of machine learning is that it could accurately assess hidden patterns among risk factors by analyzing large data set. And they are mostly effective when a large amount of data is available for the training phase of the algorithm, and this is not the case for example, in the early phase of the outbreak. And as in the previous day, as yet been observed, Machine learning are often black boxes which are hardly interpretable. But we'll see in the next slides more in detail these points. But first, I would like to give you a definition on what is machine learning and deep learning, even if the speakers in the previous day gave this definition yet, but we'll do a little repetition. What is that distinguishes classical programming from machine learning? In the first, so when we are talking about classical programming, we give in input rule and data, and we obtain in output some answers. Meanwhile, with machine learning, we give in input data and answers, and we want as a output rules that link output and input. What is deep learning? Deep learning is a subfield of machine learning, and to better understand, if we look at a simple neural network in the right side of the slide, we can say that red dots are input data, blue dots are output data, and the yellow dots are layers in which data transformations are performed by the algorithm to find a better representation of data in order to extract useful rules to link input and output data. And if we look right, we have a deep learning neural network, which in a nutshell means that I have a neural network with more than one layer of yellow dots, where such data transformation are performed to obtain a meaningful representation of data. Here we can see an example of an application of deep learning to COVID-19 epidemic, where the authors used a convolutional LSTM, which is a sort of merge of two algorithms of deep learning, which are convolutional neural network and non-short-term memory. The first is mainly used when we are dealing with images, and the second when we are dealing with time series. So this kind of algorithm allows us to treat the forecasting of COVID as a spatio-temporal problem. So these authors divided Italy in a grid, and they made the forecasting using such a spatio-temporal approach in an autoregressive way. It means that they used the time series of cases to predict cases, and they obtained the promising results. So following this idea, my colleagues and I used a convolutional LSTM for a spatio-temporal forecasting of new cases and new hospital admission of COVID spread in Reggio Emilia, which is in northern Italy. But we don't use only an autoregressive model, but we incorporated also satellite information about pollution, meteo, and mobility, using artificial intelligence algorithms that allowed to extract such kind of information from satellites, thanks to the support of the European Spatial Agency. So using such kind of approach, we were able to make a prediction on a grid with a cell with an extension of 12 kilometers square, and we were able to take into account spatiality and temporality, and to consider the conditions of the neighborhood of a cell, and to make a prediction to a very local level with such extension of 12 kilometers squared. And this could be helpful to better allocate resources, and we obtained very promising results. And such algorithm is yet implemented in a web tool, and it is used by decision health authorities as a support. And without artificial intelligence, such kind of work is hardly feasible. Deep learning have been widely applied for COVID-19, mainly when we are dealing with a kind of data that is not traditional. For example, it has been used for computer vision, like for medical image analysis, ambient intelligence, or for natural language processing, like to deal with medical text note or to do public sentiment analysis, for example. Machine learning have been widely used for COVID-19 outbreak. And as we can see in this systematic review, convolutional neural network were the methods more used for medical imaging. And for example, for diagnosis of COVID patients from, for example, pulmonary X-ray. Meanwhile, random forest was the best used algorithm to choose the best feature for classification. Here we have another review published recently, which underline basically the same thing. I mean, we can see in this image the general framework of using machine learning and deep learning technique in COVID-19 diagnostic and prognostic prediction. And even in this case, we can see that CNN was the most used algorithm when dealing with imaging, and random forest when dealing with non-image based predictive modeling in COVID, using, for example, data about vital sign or lab test. Getting closer to the final remarks, I would like to suggest you this reading because it is a very easy reading for PhD students. It could be good. And we have a pro-con debate for machine learning versus traditional statistics in COVID-19 prognostic models. And it is presented and discussed in a very easy way. For example, in this image, the authors underlined the strengths and the weaknesses of machine learning and classical statistics. For example, machine learning is useful when dealing with high-dimensional data, such as images or text that could be unstructured data. Meanwhile, for example, classical statistics is easily interpretable. I mean, the larger the coefficient, the greater the impact on the outcome, generally. But machine learning often leads to very accurate prediction model, identifying also complex nonlinear correlation data. And on the other hand, classical statistics leads to biologically plausible models, easily interpretable. In fact, the starting criticism of neural network is that their hidden mechanism may provide rules that have no plausible relevance. Meanwhile, regression analysis can provide causality, and it is easily interpretable. In fact, as we can see in the image on the right side of the slide, which is extracted from the book of Robert Ifshiran, that was our speaker in the first day, we can see how greater the flexibility, lower the interpretability. For example, deep learning has a very high flexibility. It is very accurate, but we have a very low interpretability. On the other hand, machine learning can find complex relationship within a forest of data, which is a task that is difficult with classical statistical technique. And predictive models in healthcare that utilize a large data set and a large amount of number of parameters have demonstrated to improve the performance with machine learning algorithms. And today, the explainable deep learning is recently become an active area of research. Researchers are studying how improve visualization methods to make these algorithms more interpretable. Or, for example, many researchers are studying more in detail the attention mechanism, which is a mechanism in the deep learning methods to analyze the time series that allow to understand which events in the past are more useful for the prediction of your outcome. And finally, machine learning algorithms can be used to predict also multiple endpoints from a single feature set, which is difficult with the classical statistical analysis. So in conclusion, the key message of my talk would be to stimulate your reflection about the point that less flexible models are more interpretable and are more suitable in the inference context where we are most interested in understanding the relationship between input and output. On the other hand, more flexible models are way less interpretable, but results can be very, very accurate. So in conclusion, depending on the problem we are working on, we may have to pick the model that best serves to our case. And in conclusion, think about George Box's statement, which states all models are wrong, but some are useful. So thank you very much for your attention, and I will leave the floor to the next speakers.
Thank you, Veronica, for your nice presentation of machine learning application in COVID-19 and the issue of this kind of technique. So Danila, she's the next speaker, Danila Azzolina. She's assistant professor of medical statistics at the University of Ferrara. And she worked quite a lot during the pandemic on COVID-19 Italian data. And so now she will present talk about machine learning to improve prediction of COVID-19 epidemic behavior. So please,
Thank you, Paola. I'll try to share with you my screen. Okay. You see the screen? Yeah. Okay. Thank you, Paola. Thank you, Veronica, for your introduction. Today, I would like to show you some issues about machine learning in predicting COVID-19 epidemic behavior. I would like to show you something like a journey, which is the COVID-19 ETA group journey among the COVID-19 epidemic data research. This research group is led by Professor Gregorio of the University of Padua in collaboration with the University Professor Paola Berchialla of the University of Turin. And our journey starts during the first day of pandemic in February 2020. Our first product was a web application which is aimed at communicate the leading indicators of the COVID-19 pandemic to the general public. However, during the first days of pandemic, especially in the Veneto region, which in Italy was the first region involved in the COVID-19 epidemic, several preventive prevention policies were implemented. So our effort was tailored to perform a change point detection analysis in order to model the possible possible impact of early prevention policies. So, however, especially during the first phases of a pandemic, generally there was several efforts provided in the literature trying to model the epidemic behavior using different parameterization. Especially different efforts were performed to predict, for example, some important parameters, for example, the epidemic peak. However, we demonstrate in our analysis how does perform the different model in adapting to the epidemic behavior according to the amount of available data. However, during our investigation, we realized that the harder epidemic indicator of the impact of COVID-19 on the healthcare facility in Italy and all over the world is in general, the number of hospital admission, and in particular, the number of COVID-19 admission in intensive care unit. So we tried to develop, we developed a predictive tool based on time series model, exponential time series model. However, this is something referred to an ecological point of view of the epidemic. However, we have to take into account that generally during the expansive phases of the epidemic, physicians in intensive care unit are dealing with a severe situation concerning the clinical pathway of patients. In this general scenario, machine learning techniques are useful for us in order to predict the possible prognostic outcome of patients admitted generally in hospitalized and the patient admitted in intensive care unit. We propose several applications to the Veneto region by using both classical machine learning method and super learner ensemble method. Let's start with the first phase of our journey. Our first product was a web application, which is aimed at communicate to the general public, but also to the expert public, the main indicator of the COVID-19 pandemic behavior. Several in-deep sections have been proposed in the web app, reporting also explanation which are easy to communicate also to people which are not expert in the field. Our first, moreover, our first efforts was tailored to perform an analysis of the first prevention impact of the epidemic policy in the Veneto region. Why Veneto region? The Veneto region was the first, one of the first region involved by the pandemic in Italy, and early prevention policies based on quarantine were implemented in this area. So we perform a bias and change point detection analysis. This, the analysis is based on the definition of a change point on the initial phases of a pandemic curve. So the change point has been identified, then a quadratic model basically has been estimated using the data until the change point identified. Then the model has been projected forward until the 27th of May. So by comparing the estimated number of hospitalization with the observed number of hospitalization, we obtained the results that as of 27th of March, 658 hospitalizations were were avoided. So this first effort was provided in order to communicate to the population, but also to decision makers, the possible impact of the first prevention policies performed in the Veneto regions. However, we was in the first weeks, in the first month of the pandemic. So the situation was really uncertainty, and several efforts were provided by scientists, data scientists, and also statistician, epidemiologists to forecast the peak of the pandemic curve. However, our analysis was based on a comparison among the most applied epidemic model. There is a strong leading comparison between the stochastic compartmental model, as introduced by Veronica, and the data-driven model, classical models, and series models. Our question was, how does this model perform depending on the amount of available data? So we apply the models to the time series of the total cases in Italy. Basically, this is the application of the exponential and the quadratic time series and the quadratic models to the total to the time series of the total cases in Italy. We have an idea that we use different fraction of the time series in order to understand what is the performance of our model depending on the amount of data used in our analysis. For example, the data until the first 20 days have been used to estimate the model, and then the model has been projected forward. The same thing has been repeated for the 3rd day, 14, 50, and so on. So in this case, we may observe that the exponential models which fit in a suitable manner during the very first days of pandemic go easily out of control, because this kind of parameterization is not able to capture the curvature of the epidemic growth. However, quadratic models, which is another classical application, is more able to adapt the curvature to the prediction to the curvature of the pandemic, especially when we have more data to estimate our model. For example, starting from the having at least 18 days of data. However, our question was during the first wave of pandemic about the performance of the most used model based on a logistic shape curve. As showed also by Veronica, this is an example of a logistic regression model estimation by using different fractions of the data. We have an idea that if you, as you can see in the picture, if we use few data to estimate our model, it is difficult to predict a pandemic peak. It is possible to incur in misleading results. We demonstrate this also in our web application. As you can see, I would like to show the interactive tools. In this case, we provide the application in an in-depth section of the web app. In the method, you can see we are analyzing the impact of the uncertainty of the estimation in a logistic regression model on the prediction of COVID-19 behavior. as you can see, you have the carrying parameters, which define the maximum fraction of population which may be infected, the N0 parameters, which define the number of initial cases, and the growth parameters. In this case, we was near to the peak, but if we move the sliders on backward or forward, also of a few amount of range, you can see that there is something misleading concerning the prediction of the epidemic peak. Especially this is true for the regions of the southern Italy. In southern Italy, in the early phases of pandemic, few cases were observed. So in this case, the attempt of predicting a pandemic peak may be easily misleading. So the key message is that we need more data to characterize the pattern of the pandemic behavior. However, another going on in our investigation, we realized that the key indicators of the impact of the COVID-19 on the healthcare facility in Italy and all over the world is the admission in hospital and in intensive care unit. Why? Because the intensive care unit admissions is an indicator which is based on a short lag effect. We have the idea that the time intercurring from the contagion until the death is higher, 20 days, for example, in comparison with the time intercurring from the contagious until the admission in hospital and intensive care unit. So it is an immediate, this indicator is an immediate indicator of the impact of severity impact of the epidemic in on healthcare facilities. So moreover, this indicator is not affected by the testing policies biases, because we have idea that in Italy and I think all over the world, it is there are different testing policies, more or less inclusive, depending on the geographical area and also depending by the pandemic period. So we realized that the intensive care unit, together with the hospital admission, is the leading the key indicators. So it is important both to monitoring the impact of epidemic on ICU by performing a timely and adapted analysis on the time series, but this is from the ecological point of view. It is also important to improve the decision-making process for the patients of the physicians that are leading with the uncertainty of dealing with patients admitted in intensive care unit. In these cases, machine learning methods are useful to improve the prognosis, the prediction of prognosis for patients admitted in intensive care unit. And we provide 2 examples concerning this. For the first side of the coin, it is important to monitor the impact of pandemic on the intensive care unit facility. We choose to develop our estimation tool, a time series model. A time series model, which is an exponential time series approach. This approach is based on the combination of error, trend, and seasonality. Each term can be arranged in an additive additive damped and multiplicative manner. The ATS parameterization is useful because give most weight, most importance to the last data near to the forecast window. So in this case, we can obtain an estimation which rapidly adapts to the last changes of the epidemic time series. However, I would, in this picture, you can observe our proposed tool. We propose a forecasting tool for the epidemic time series of ICU admissions in Veneto regions, but the web platform provide the same application also for the other regions. As you can see, basically, this kind of model, the red line is the expected, the blue line is the observed, is easily adapted to the changes of the pandemic. So the red shaded area indicate the confidence interval bounds. So this is useful for physicians in intensive care units, which could monitor the impact of pandemic easily concerning the intensive care unit admission. However, our analysis is tailored also to the patient's level. It is important also to assess and evaluate the effect of the pandemic on the patients admitted in intensive care unit. Machine learning method could be very useful for us in this field of applications. In this picture, you can see the comparison among the classical statistical model and machine learning models. As introduced also by Veronica, we may observe that machine learning models are tools which are more based on an algorithmical structure and elaboration of the data. So these models are more tailored to improve, to optimize a predictive accuracy, and generally deal also with high dimensionally data, and also not easily coded data, for example, images and free text data and so on. From the other side, the classical statistical approach are useful for from an epidemiological point of view, because give us the possibility to interpret in a more open manner the impact, for example, of the risk factors for the patients on the pandemic, on the potential outcome. So it is a more interpretable tools. However, machine learning method concerning COVID-19 predictive prognosis is very useful because it gives us the possibility to perform a risk stratification analysis for the patients referring to the intensive care unit according to its characteristics. We have also the possibility to use big data and analyze a huge amount of data, using data that are heterogeneous in their nature, for example, images and also free text data. This provided tool may assist the physician in their decision-making process, especially in a situation of uncertainty and in urgent situation. Obviously without substituting the human decision-making process. However, the first example that I would like to show you is an application of a classical machine learning method to the prediction of the in-hospital mortality of an important referring center of the Veneto regions in the Padua district. In this case, the study design is a retrospective study, which is include a patient affected by COVID-19, referring to the ospedali riuniti of Padua in Italy, admitted from March until April 2020. We collected some demographical information, social demographical information, medical history, clinical lab data, and so on. And our prediction outcome is the intra-hospital mortality. What are the model considered in our analysis? We considered the classical machine learning method applications. In the violet identified models are the basically the three basic models. The support vector machine serves as comparison tool. In this case, on the right side of the screen, you can see the images representing the mechanism of the algorithm. For example, the first one, the classification and regression tree, is an algorithm, a single decision algorithm, which is based on the recursive partitioning process of the data, which is aimed at optimize minimize some entropy function in order to obtain a suitable prediction. However, in some cases, basically this CART, classification and regression tree algorithm, suffer from overfitting. So it is useful overfitting because they are much more over-adapted to the data. So to generalize our conclusion, may be useful to combine the results in a big ensemble machine learning method, for example, the random forest model. Random forest model is based on the combination of several classification and regression trees, which have been trained and tuned in a parallel manner. However, also the gradient boosting machine has been considered. Also, the gradient boosting machine is a machine learning method which is based on a classification and regression tree. And the mechanism, the growing mechanism of the algorithm in this case is not parallel, but is sequential. We start from a most simplest algorithm and then complicate the algorithm in a sequential manner. The super vector machine serves as a comparison. In this case, the algorithm is based on the optimization of the separation among the classes based on the optimization of hyperplan margin. This is an example in the picture of a linear separation, but other separation function may be provided. The predictive tools were tuned using a bootstrapping algorithm within 50 runs. Basically, there is a distinction between the single algorithm, recursive partition tree, for example, the bugging algorithm, random forest, which is based on the parallel estimation of single regression tree, and the boosting algorithm. The boosting algorithm grows the final model in a sequential manner. What concerns the results of our estimations, the results, the top side of the screen is reported the performance in terms of F statistics and receiving operative characteristics curve, and we report the results within the bootstrapping iteration. For these reasons, we report the histogram. It is evident that the random forest ensemble approach give us the higher performance in terms of receiving operative characteristics and other performance indicator. We propose to the clinicians. Also, a ranking of the variables. Another issue, important issue of machine learning method is the possibility to give to the clinicians a ranking of the variables involved in the algorithm concerning their importance in predicting the final outcome. In this case, the age, creatinine, AST, and oxygen saturation together with the lymphocytes are the leading predictors. We propose to the clinicians and another web application for the prediction of the in-hospital mortality. The application has been developed in a shiny environment and hosted on the University of Padua repository. However, the clinicians could fill the characteristics of patients and return a results, which is an outcome prediction in terms of probability of in-hospital death. Another example, combine the machine learning model in a super learner approach. This is an effort in predicting the COVID-19 intensive care unit mortality by applying a machine learning approach using a super learner algorithm. The super learner is an ensemble machine learning method which is aimed at combine several algorithms in order to improve the final performance of the estimation. So the procedure is based on the parallel runs of several algorithms by using a cross-validation procedure to evaluate the final performance. However, in its original formulation as proposed by Paola, this algorithm is based on the stacking procedure. Basically, it is an averaging of the performance of different algorithms that rather than complicate the procedure via boosting or bugging procedure. For what concerns our application, we apply this machine learning method in predicting the ICU intra-hospital mortality for the data provided by the intensive care unit network for the Veneto regions. 1,293 patients were admitted to the intensive care unit from October until the 4th of March. This data served as model training data. Another group of patients, 124, served as test set data, which is composed of patients admitted in intensive care unit in the for the COVID Veneto ICU network from the 7th of April, from the 5th of March until the 7th of April. Another external set of data, test set 2, has been considered as a test set, and has been it is a data set provided by the Lombardy regions. How these are estimated different models. The first model was tuned and trained by considering only the futures, the variable having at least the 85% of the data. The external validation in this case has been performed on the first test set 1. However, the second model was tuned by considering all the variables collected in the ICU without considering the percentage of missing data. The external validation was performed in this case on the test set 1. The model 3 was tuned on the both variable collected in admission in intensive care unit and also variable collected during the intensive care unit hospitalization. The external validation was performed also in this case on test set 1. This is the representation of the variable involved in the different models. For the model ones, the models ones is very simple, involved also 5 features identified by the most filled variables provided by clinicians. Instead, the model 2 has been trained on a more extensive set of features, including also all the variables generally more or less include identified on the patients in intensive care unit admissions. The model 3 includes both all the variables included in the admission and also the features, as you can see, which generally have been collected during the hospitalization period. The tuning of the algorithms involved in the model has been performed by using a cross-validation procedure. The cross-validation procedure divides the set of data, in this case a 5-fold cross-validation divides the set of data in 5 different folds. For the first fold, for example, we consider the first 1/5 part of the data as a testing set. The other part is the training set. For the second fold, we re-perform the procedure, but in this case, we consider the second 5 part of the data as a test set, and so on. So the final performance has been obtained by basically by averaging across the performance achieved within the cross-validation fold. The machine learning method included in the super learner approach are those represented in the left side of the screen. Classification and regression trees, random forest, gradient boosting, bugging, general bugging models, logistic regression, Mars models, generalized additive models, neural network, simple neural network with one hidden layer, super vector machine, and also nonlinear least square. This is basically the algorithm most used for classification purposes, which are combined in a superlearner algorithm. Okay. Also in this case, we provided for the clinician a web applications. We give the possibility to the physician to choose from different models. For the model set 1, basically the clinicians could estimate the probability of intra-hospital ICU mortality by filling only the 5 variables characterizing the most simple model. Otherwise, if the clinicians has the availability of much more data, could fill the prediction within the model set 2 panel. Otherwise, if all the data, complete data are available for the patients, the clinicians could fill the model set 3 panel and obtain the intra-hospital mortality probability. What about the model performance? As expected, in this case, you can observe the model performance for model 1, model 2, model 3. For model 1, it was possible to validate the model on the training data via cross-validation procedure on the external validation court of the Veneto regions and also on the external validation court of the Lombardy regions. Model 2 and Model 3 have only the training performance validation and external validation performance. We can observe that, as expected, the higher performance in terms of receiving operative characteristic curve and also the other indicator is achieved by the model 3 with 0.93 on the training data and 0.81 on external the external testing data. However, it is interesting to observe that for the model 1, even if we have only few variables to estimate our model, the prediction performance is still acceptable. So we provide to the clinician the possibility to perform the prediction, still reliable prediction, even if we have a few variables to estimate the patient's profile. For what concerns the variable importance plot achieved by super learner algorithm, as expected, basically the age is the leading predictors for all the model considered. For the model 1, the most simple, the SOFA score is the leading predictors. Instead, for model 2, we had following the age, obviously. Instead, for the model 2, the palliative performance score has an high importance in the ranking of the variables. Otherwise, also in model 3, which is the most performant, basically. In the model 3, the leading predictors are the age, the saturations, and the palliative performance score. So, for what concerns the results, we estimate as a model providing a tool for predicting the inter-hospital mortality in COVID-19 patients admitted in intensive care unit by using data provided from a large sample of patients. So the super learner, basically the super learner approach has been shown to be a feasible approach used applied to clinical data in order to achieve a good predictive performance, even if we have a few variables to estimate our results, and a good generalizability because we validate our model also on external validation sample. For what concerns the general finding of our journey, the process is still ongoing. We may go in deep in analyzing what are the machine learning method which give us the optimal solution in terms of prediction of the patient's outcome. We may also try to investigate the performance of other algorithms as indicated, for example, also by Veronica, the deep learning approach and other approaches applied to the setting of, for example, of intensive care unit. Moreover, there are other possible future research development concerning the possible linkages between machine learning methods and the prediction of epidemic time series trend. As previously indicated, in this case, we need to a higher amount of data to estimate this kind of prediction. Data provided by satellites or provided by by satellites and other data provided by official sources. So this is another future research development. So in all cases, the choose among the optimal solution depend on the epidemiological purposes of our analysis, and the possible solution require for us other future explorations. Thank you all for your attention.
Thank you, Danila, for your presentation, for your nice presentation. We have some burning question. I just would mention this question because they are very much related to your super learner model. And the question are about missing value. How you have dealt with the issue of missing value, and if you have tried some kind of sensitivity analysis to understand the impact of the amount of missing value.
Yeah, sure. Yes. Basically, we perform some sensitivity analysis which are not included in the final paper. We observe that basically by performing a suitable imputation method, for example, in our analysis, we use the hot-deck imputation. By using a suitable imputation method, there is not a huge differences between the amount of missing data, starting from a percentage more or less of, if I remember, of 17%. However, the distinction, a little distinction of the final results, there is in the case of using a complete cases analysis. If we use a complete cases analysis, in this case, the final performance could be affected. We have idea that the missing data mechanism and pattern in an intensive care unit admission, I have idea that could not be assumed as completely missing completely at random, because sometimes the data are not available because there are difficulties for collecting data, especially in an emergency situation. So in this kind of analysis, we have to take into account these issues, performing a suitable imputation method. And with a suitable imputation, we can deal with missing data even if we have a consistent amount of missing. The importance of in this kind of model is to include the relevant features that are linked to the final outcome. So the percentage of missing data is an issue which could be easily handled by performing a suitable analysis. Yes.
Okay, thank you. We can skip the other question to the floor discussion. They are much more global question. So thank you again, Danila. And now we can give the floor to Professor Laure Wynants. I hope the pronunciation is correct. Laure is Assistant Professor of Epidemiology at Maastricht University and TU Leuven in Belgium. And since the beginning of the epidemics, she is leading a consortium, an international consortium, which is doing a systematic review of model for COVID-19. And I would recommend, I won't recommend all the participants to read the Laure systematic review about the prediction model for diagnosis and prognosis of COVID-19, which is published by BMJ. And this is a living review, which I think is an outstanding example of evidence-based information for public health decision-making, and which was also used by European Commission, WHO. So it's really an important and great work. So thank you, Laure, for accepting our invitation, and please, you can share your presentation.
Thank you for the very kind introduction. I hope my presentation, you can see it and you can hear me well. Yeah, all right, let's get started then. So what, let's see if what are we going to talk about today? Well, first I want to clarify the type of models or the type of AI that I'm talking about here. Victoria already explained some of the different types of AI that you can use in a pandemic. I will clarify the ones I will address. Then I will motivate our decision to do a review of these models. And then, of course, I will explain how and when we did the review and discuss the results. And then I want to have a more general discussion about the results because a lot of the results that I will show you will focus on bias in these models. And I want to tell you what I mean when I say bias. And from that discussion, I want to draw some lessons for the future. How can we advance this field of AI and prediction and machine learning and statistics? So what type of AI models are we talking about? Well, we heard already in the previous presentations that there are several methods that you can use. Some are more linked to machine learning or artificial intelligence. Others are more linked to traditional statistics. But actually, if you look in a policy context, it's very broadly defined. And all of these are considered AI in health. It's not so narrow. So anything that you use to make a prediction or to recognize a picture that can help in making a diagnosis or prognosis and support decisions, all of that is considered AI in health. So what we have here is my working definition. So any model that is data-driven, that combines several inputs or several characteristics, and then gives you a prediction for individual patients, I consider that a diagnostic or prognostic model. So diagnostic, for example, for diagnosing COVID-19, prognostic for predicting what happens to this patient in the future. That includes a very broad spectrum of models. So that includes anything going from a scoring rule that a clinician defined based on looking at some descriptive data until deep learning and everything in between. So very broad definition. And if we use such a broad definition, it's actually inevitable that you come into conflict with some terminology. So maybe you will catch me using some of these terms as interchangeable as statistics and epidemiology and machine learning have been using different words to mean the same thing. So for example, prediction or supervised learning, or an outcome variable or dependent variable or targets, or a predictor, which is actually the same thing as a feature. So depending on your background, this could help. So why would we review these models? I need to make a quick change here to my screen. Okay, why would we review these models? Well, you've all noticed this. This is probably also the reason that you're having this winter school. AI and machine learning is really everywhere. You can open any clinical journal, or you can open even newspapers, and you will read about how promising AI and machine learning is for medicine. Some even go so far to suggest that doctors may be replaced by AI system and that will improve your diagnosis or prognosis. That's a bold statement. But in the context of COVID-19, especially in the beginning of the pandemic, it made sense for me to learn from data. Because in the first months, it's long ago, March 2020, doctors didn't know what hit them. This was a new disease, and there were a lot of large questions regarding what is the optimal management, what's the prognosis of these patients, what is risk factors, how can we make the diagnosis. There was limited testing available. So this was an excellent opportunity for machine learning and for AI and for statistics to prove that they can learn from data and help support decision-making. If there was any time to show their benefit, I think it was now. And you see this because very often, very quickly, very soon, prediction models started popping up for COVID-19. There was interest from academics, from companies, from governments, and some of these also made it into policy. So in the UK, there was a prediction model developed. It was used on the entire population, and it was decided based on these individualized predictions to send people who were vulnerable a letter that they should shield. And in the United States, there are FDA approved algorithms that can be used in intensive care units to monitor the progression of patients. So I told you why it's interesting. But then why review the models? Why not just make one myself? Well, we have to realize that a good model could improve care and reduce the costs. We've shown this in other diseases. There are impact studies, clinical studies, trials, experiments, health technology assessments that show that prediction models can help because they target the right care to the right patient. So when resources such as beds and tests are very scarce, it's obvious that there's a lot of potential here. You can help allocate the scarce resources. But there's another side to this point, and this is very important. Inaccurate predictions can actually lead to harmful decisions. So you can do worse with a prediction model than without a prediction model. And there is a concern, there's a precedent. So ICU scores during the swine flu pandemic, they worked, the same scores that usually work very well didn't work during this pandemic. So the question obviously is, can we trust algorithms during the current pandemic? So the fact that inaccurate predictions can lead to harmful decisions is easily demonstrated by this study. So this is a deep learning model for the classification of liver cancer. And what you see is that there's a little bit of danger to decision support system based on data-driven algorithm. Because what you see here is that the impact, if the model is correct, is positive, but it also, if the model is wrong, it influences the clinician and it makes their decisions wrong compared to when they don't have a model. So it's always a risk-benefit assessment. The potential is there, yes, but are we doing more good than harm? It's a crucial question. So what did we do? In March 2020, we started looking into the models that were being proposed. And we started pretty quickly a systematic review. The first one was, there was a preprint with the first results also in March. And then early in April, we had our first published version. Then we were, because the field was moving so quickly, the BMJ asked us to keep updating it. So we've published a few updates since, and we're still working on it. So what did we include? Well, we included peer-reviewed articles. And in the first few updates, we also included preprints. And that is, the reason is obvious. It was going so quick that the traditional publishing was too slow. So we had to include these preprints. But later on, because the review was going so large, we didn't include them anymore. And we included 3 types of models. So the first one are the models for susceptibility. So in the general population, people who are currently healthy, who's at highest risk to develop COVID and develop bad outcomes from it. The diagnostic models, so for people who present because they have a high-risk contact or because they have symptoms, so the diagnostic models. And then for people with highly suspected or confirmed disease, what is their prognosis? So for each study that we included, we had 2 independent researchers. These looked together at each study, and they extracted the data from the models described in the study. And if more than one model was described in one article, they assessed each model separately. And for this data extraction, we used existing checklists. So the CHARMS checklist, which tells you which key characteristics of prediction models you should extract from a study, and the PROBUS risk of bias tool, which helps you ask some critical questions about the study. So in the updates that we've published so far, we have included 37,000, or we've screened over 37,000 articles. We've included 170 studies, and together they proposed 236 models. 11 of those were to identify subjects at risk in the general population. 118 were diagnostic models, and that includes models based on images and models that make a classification in terms of disease severity at presentation. And then we have the prognostic models, for example, to predict during the course of the disease who will die, who will progress to a more severe or critical state. And if we look at the characteristics of the models that we have reviewed, we see that, most of them use data from one country only. Very often, keep in mind, this is heavily influenced by the beginning of the pandemic. So a lot of these studies came from China, but there are also international data sets. And nowadays, these models are developed all over the world. Most of the models that we saw were developed for hospitalized patients, and that is easy to understand if you know that that is where most of the data is being collected in a systematic way. So patients from general practice are not, well, there are barely any models for patients in general practice, and most are models for confirmed or suspected disease. What's important to note is that about half of the models are already available, or at the time that we reviewed them, were already available in the format for use in clinical practice. That means that anyone could go to a website and check or fill in predictions or get predictions for their patients, or the algorithm was available in some other way. So they were out there. The methods that were used, and this is also interesting, I think, about a third are the very traditional regressions, logistic regression. Another third is the very advanced deep learning, the very complex algorithms. And then another third was everything else. So for example, Cox, proportional hazard models, support vector machines, random forest, etc. In terms of included predictors for the diagnostic models, that was the top 5 were vital signs. Very important here was fever, flu-like signs and symptoms, the age of the patient, electrolytes, image features, and for the prognostic models, that was age, comorbidities, vital signs, image features, and sex. Let me get a sip of water. Yeah. So what you all want to know, of course, is how well do these models do? The C statistics, that's the area under the ROC curve, if you talk about a binary model. That describes how well the model can distinguish between people with and without the event that you are looking for. So for example, patients who do and don't die, or patients who do and don't have COVID. And a value of 0.5 is no better than random. A value of 1 is perfect. And you see that for each class of model that we've looked at, we have models that do near perfect. So that would be a cause of mass celebration, especially early on in the pandemic, because it means that you don't need PCR testing. You know exactly who will need an ICU bed, etc. But the real question, of course, is can we trust the predictive performance that was reported? Can we trust this? And this is what we found when we asked that question. We found that only 4 models were low risk of bias, 6 were unclear risk of bias, and 226 were at high risk of bias. And you see that this problem is present for each type of model that we looked at. So for the imaging models, for the diagnostic models, for the prognostic models, they all suffer from risk of bias. So then what is bias anyway? That's a very a statement that I can make, but you have to understand what I mean. And if you ask bias in machine learning in health or bias in prediction in health, depending on who you ask, you will get another answer. So if you ask a policymaker or an ethicist, they will often think immediately about bias and fairness, for example, social bias or racial bias or gender bias. Well, I have to say that we haven't looked at that. A machine learner, if they speak about the bias term or prediction bias, they often mean the difference between the average of the prediction and the average of the labels. A statistician would call that miscalibration. We've looked at that, but that's only a part of what we've looked at. So that's not a complete definition either. And a statistician, when you ask a statistician, well, they will say that bias is the expected value of the difference between your estimator and the parameter that you want to estimate. So it says something about how wrong you are on average. This is also only one part of what we looked at. So an epidemiologist, if you ask an epidemiologist what a bias is, they will tell you it's the error that leads you to being wrong. So for example, an error in the design of a study that leads to conclusions that are systematically different from the truth. And epidemiologists really love bias. They have invented a whole catalog of it, and they found so many types of biases, and you can look it up. But let's come to the point and let me tell you what we define as bias. So according to the PROBAS risk of bias tool, bias is risk of bias occurs when there are shortcomings in the study design, the conduct, or the analysis that can lead to systematically distorted estimates of a model's predictive performance. So this is what we use to answer that question of a reported predictive performance. Can we trust that, or is that probably too optimistic? And this tool has signaling questions in 4 different domains. So there are questions about the participants, about the predictors, the outcome, and the analysis. So if you look at our results, you see that quite some studies had issues with the participants, and also that means that there are problems with collected data. So the participants that they included in the study were probably not representative of the target population. The predictors and the outcomes, this is less frequent, but also here we saw problems with the definition of or the measurement of these variables. Like an example from the outcome, a really strange one, I still think, is that there were models out there that were being marketed as COVID-19 models, but they're actually exclusively used pre-pandemic data, for example, on other respiratory illnesses. And then the most problematic domain, that was the analysis domain. So the top 3 errors in this analysis domain were an inadequate sample size, model performance measures that were not correctly or not completely assessed, and optimism. So I'll walk you through some examples to show you what these errors can look like in practice. So this is one example of a study. And here the goal was to build a model to predict mortality. But you see that the model had data on only 19 deceased patients to learn from. Now, if you have a model that learns from data, 19 cases is not a lot. In our review, we actually found that most studies had just a few hundred patients. And an event, that's the outcome you're trying to predict. So for example, COVID for a diagnostic model and death for a prognostic model that looks at mortality. So the median number of events was 70, which is also not a lot. These numbers on its own don't give us much information, because you always have to look at the sample size in the context of the modeling strategy that you're using. But actually, we've seen that 70% of papers that we've reviewed had insufficient data for the chosen modeling strategy. So sample size was a crucial issue. So the next error was model performance measures. So what did we see? Well, here's an example of a model that predicts the need for mechanical ventilation. And on this graph, you can see the RSC curves. You can see that for the model that they propose, it's very close to the top left corner, which indicates that this model does an excellent job at distinguishing between who will need mechanical ventilation and who will not need mechanical ventilation. But if you then look at the right-hand plot, you do see that there are some issues with this model. If you read from what this plot shows you is how the predicted probability of the need for mechanical ventilation corresponds to the observed probability, the observed risk for these patients. And at the red arrow, you see that the predicted mortality risk or mechanical ventilation risk of roughly 2% corresponds to an actual risk of over 10%. However, most models or most studies never assess calibration. They'll only show you this. And in fact, most models, 68%, do not give you an appropriate evaluation of both discrimination and calibration. The next problem that we've encountered was optimism. So when you give a predictive performance, you will always have to be sure that you are not over optimistic. And for that, you need a reliable validation strategy or a reliable testing strategy. Now, the majority of models were only internally validated, for example, using bootstrap or cross-validation, or not validated at all. And even if they used internal validation, this was done often in an inappropriate way. So here you see that these authors, in this example, they use a genetic algorithm to select which predictors would go into their model. And it looks very complex and very impressive. But what's important, what you should note, is that the test split was only set aside after the predictors for the model were chosen. So this biases your predictive performance estimate because you already used information of what's important in your test set. And in fact, 53% of studies used or had issues like this, where the optimism was not appropriately accounted for. So these were the top 3 errors, but there are also some other noteworthy problems. So what we often see is that time to event outcomes are dichotomized and all censored cases are thrown away. So in this example, they threw away more than half of their data. Another interesting one is predicting death, but not putting any restrictions on when your predictors are measured. So that often happens when researchers try to predict in-hospital mortality using electronic health records. So in the example that I show here, the researchers used the lowest oxygen saturation during the stay as a predictor. And you can get very interesting patterns in the data this way. So you will see that a number of patients had an oxygen saturation of exactly 0%. And it happened only in the diseased patients. So that's not even plausible in diseased patients. I'm not a medical doctor, but I talked to some, and they say that it's very likely that the oxygen saturation fell below the limit of detection of the oximeter in these patients. So you have to ask yourself, if you're doing a decision support system, if that is your goal, are these predictions still useful to a doctor? So what is actually happening here? Are you predicting death, or are you diagnosing that the patient is in the process of dying, or perhaps even already dead? So that makes the prediction of mortality misleadingly easy. Another one is a word I like. I didn't invent the word, but Frankenstein data sets. So that means throwing together all sorts of data sets, and often data from the cases, the people with COVID-19, come from a different source than the data from people without COVID-19. So here you see a study. They tried to make models that distinguish between COVID and non-COVID based on CT images. They included data sets that they obtained by doing an exhaustive search of data available online on the internet. And we saw this very often, especially in the deep learning studies. Now, there are some issues associated with this approach that you should be very aware of. First of all, of course, the cases and the controls, they call it controls, but it's of course not a real case control study, but the cases and the controls, they differ in many ways, and this can lead to spurious correlations in the data. So one of the most frequently used data sets of controls was data on pediatric patients. So what does your model learn then? Does it learn to distinguish between COVID and non-COVID, or between kids and adults? Another example is a mix of data of patients lying down or standing up. And what typically happens is that the more severely diseased the patient is, the more likely it is that this patient will be scanned laying down. So what happens is that the model is not learning whether it's COVID or not COVID, it's learning the position of the patient while the scan is taken. Another one is, another interesting one is that in hospitals that are heavily hit with COVID, you always have hospitals that are more and less hit with COVID, and the machines start learning the hospital's text font on the scans instead of the disease. So they're distinguishing between hospitals instead of patients. Another issue with these Frankenstein data sets is that people mix and match data sets that they find, and they don't realize that one of the data sets was already a combination of existing data sets. And that way, sometimes the same image is included more than once. And if you then do a train test split, you can have the same image both in the training set and both in the testing set. And also this inflates your performance. And the last issue that I want to draw your attention to is that it's often in these situations, the data set is not representative of the patients who get imaging due to suspicion of COVID-19. So it threatens the external validity, or at least the validity for the target use of your model. So in addition, the reporting was quite disappointing. So it was often not clear when the model was intended to be used. For example, is it at admission? Is it during the stay? It's not described. Or in which type of patients? Is it suspected disease, confirmed disease? It's often not clear at all. So the reporting was pretty bad. But of course, there's also good news. It was not all very dramatic. So Q-COVID models is one of the examples that I really like. They predict the risk of, in the UK, for people who are currently healthy, the risk that they catch COVID-19 and subsequently get hospitalized with it or die with it. And this model has been validated in a huge validation study covering 80% of English adults. And it worked very well. And it's also modified for vaccinated populations. So I want to move on to the discussion. I'm not sure how much time I have left. I trust that you will give me a warning if I'm running out of time. So in terms of discussion, I would like to echo back to what Professor Tipshirani has said, I think, on the first day. Methodology and statistics, that may not sound so sexy anymore. But understanding bias and uncertainty will always remain crucial. And with respect to differences between traditional statistical models, regression models, and more flexible machine learning models, it's often claimed that these advanced machine learning models perform better, but they are also more data hungry. So they are more demanding. And actually, if you look into the data, this is what these reviewers did. They did a systematic review of all clinical studies comparing on the same database, a logistic regression model and a machine learning algorithm. They could not confirm that indeed machine learning gives you better predictions. So the traditional models, the statistical models, often work just fine. Now I realize that I painted a pretty bleak picture of the field, especially in COVID-19. We were quite shaken by it, didn't expect it would be this bad. But I also want to tell you that these findings aren't new. So systematic reviews of prediction models have been done for many different medical applications. And the findings, although not always as bad as here, the findings are always very similar. There are many prediction models developed for exactly the same problem. Very few of them are externally validated. The reporting is not very transparent and is incomplete. And very often, there's a high risk of bias. And by now, it has also been empirically shown that these high risk of bias models lead to lower performances when they're used in new data. So was this also the case for the COVID models? Well, unfortunately, I think it was. What you see here is the results from a validation study that I was not involved in. And what they showed, they tested several models. And what they showed is that the predictive performance and the clinical utility of a model, of all of these models, to predict deterioration of a patient, was actually when the lines here drop below the horizontal line, that indicates that this multivariate prediction model, most of them included oxygen saturation, they did worse than only oxygen saturation. And that's a clear indication that there was overfitting. Same with the mortality models. So again, if the line for a specific model drops below the curve, the model is doing worse than age alone. I've also been involved in a few Ipd Meta-Analysis Validations. So Ipd Meta-Analysis means that you combine the data from several cohorts or several studies, and we validate then the models that have been proposed on all of this data simultaneously. So what we did is we had one study where we had over 45,000 patients from 18 countries worldwide. And that study is now ongoing. We have over 12,000 patients from 10 low and middle income countries. And we validated 8 and 4 models for short-term outcomes in hospitalized patients. And what we find here is that indeed there's clear overfitting for most models. So the models don't perform as well anymore in the new data sets, especially with respect to calibration, there are problems. And there's important heterogeneity in the performance between the countries. So there's no universally valid model. It really depends on the patient spectrum that you have in your setting. So the World Health Organization has looked at our review, and it recommended not to use any of these models that we've looked at for use in the clinic. They concluded that the methodology or the models were not ready for that. But a word of warning is that there are also other models available that we have not looked at. So if there was no scientific report, no published study, that was outside the scope of our review. And I can think of in-house developed models developed by hospitals. I know there are some proprietary algorithms. I know there are some of those as well. And we try to look at a few of them, and we do have some indications that their quality is not better than what we have seen. In rare cases, there's a suspicion of fraud. The least you can say is that there's no transparency. So the question really becomes, how can you know that these models work as advertised? So to conclude, I want to sum up the key lessons that I've learned from doing this review. And the first one is that the popularity of prediction modeling leads to a tsunami of hundreds of models for the same disease. The second lesson is that most of these models are of dubious quality. So looking for a good model is actually like looking for a needle in a haystack. And the third one is that too much competition can threaten the safety of patients. And I really fear that. So how can we do better then? Well, I think the first solution is to adhere to the methodological standards that are clearly described in the methodological literature. So if you're developing your model, do your best to prevent overfitting, do your best to prevent over-optimism. The second one is that, of course, data-driven modeling requires data. You see a lot of push to these, getting away from these data locked up in silos and going to what they then call data lakes, or making data more easily accessible. But I have a worry about that, because I don't think we just need more data. I also think we need better quality data and crucially representative data, because we know that performance is heterogeneous and you need to be able to understand the data in the context it was developed in. So I think we need representative data as well. Then my third key recommendation is please share your models. So I think we could have done so much better in this pandemic if we had been able to just do the validations right away. And then we could have, but because the models were often not publicly shared, the equations weren't reported, it was not possible to do an external validation. And if we had access to large databases sooner, if we had access to the model equations sooner, we could have easily done head-to-head comparisons of models, identify the ones that work best, and then update or tweak those models with updating or transfer learning to optimize them for local settings. But that wasn't possible now. And the last recommendation was to use multidisciplinary teams when you're developing a model. So what we have seen often is that sometimes models are developed by clinicians and the model is really matched to a clinical need, but the methodology is so substandard or so simplistic that it's not good enough. But the other thing happens as well. So we've seen highly complex, highly advanced models that were just not matching any real clinical need. In fact, they didn't even say what clinical problem they were addressing. So you need multidisciplinarity in this field, I believe. So what are we doing now? Well, I'm still working on the fourth update. It's really a lot of work. Even though we've already restricted to the focus to look only at prognostic models from now on, we still have over 200 studies representing over 300 new models and I think over 200 external validations of existing models. And we're also involved in some modeling work ourselves. I'm working on prognosis in primary care, a setting that's much more difficult to study because systematic data collection isn't in place there the way it is in academic hospitals. And my colleague Maarten is working on prognosis for the elderly as well in another study. This was unfunded work. So I had a very large team of very dear colleagues who dedicated a lot of evening and weekend hours to this. And I haven't even mentioned them all here, but the ones who are involved early on are mentioned here. We got a few smaller grants and support from Cochrane. These are acknowledged here as well. And if you want to know more about this work, then I invite you to go to our website. So on this website, we have details on all of the models that we have reviewed. So you can see our assessment of each of these models, but also a layman's summary of our findings, which was written with actually by COVID-19 survivors. So if you have any questions, I'm happy to take them during the discussion section. I doubt that we still have time now. But you can also email me or find me on Twitter and we can have a chat. Thanks so much for the invitation and for your attention.
Thank you, Laure, for your really great presentation. And there are a lot of questions for you, but I think that we can skip them to the floor session. So now we have the last talk. She's Ilaria Dorigatti. She's here now. Thank you, Ilaria, for accepting our invitation. I'm very happy you could find some time for us. And Ilaria is a lecturer and fellow at the MRC Center for Global Infectious Disease, the public school of Imperial College. And she's contributed to the international response against COVID-19 because she takes part of the Imperial College COVID-19 response team. So I'm very happy she will talk about the SARS-CoV-2 transmission.
Hi, Paola, and hi, everyone. Thank you for the invitation. I hope you can see my screen now. It froze. Okay, it just froze for a second, but I think it's all right now. Yeah, so thank you very much for having me. Thank you, Annibale and Patrizia, for giving me the first kind of invitation. And then thank you, Paola and Angela and everyone involved, really, for giving me the opportunity to talk to you about the kind of modeling that I do, which you will see is different from the kind of modeling that Laure has talked about so far. Although I must say, I agree with the 3 lessons that you've seen in the last email completely with my field as well, but we can talk about this at the end. So now we are talking about modeling SARS-CoV-2 transmission in VO. And I'll start with the acknowledgements, because this work would not have been possible without the help and the work of many people that has been involved. And I'm talking about people at Imperial College, the whole Imperial College COVID-19 response team, at the University of Padova and the Azienda Ospedaliera of Padova. You will see that this work is very much based in the university where you are studying now. And I'd also like to thank the funders, especially Wellcome Trust and the Royal Society, who are really funding my fellowship. That gives me the possibility to explore and to answer public health relevant questions, essentially. So give me the freedom as well to do the research that is of interest to me. I thought I'd start with setting the expectations, because when I received this invitation, the topic of the session was machine learning and prediction in COVID-19 epidemics. And I said, I can talk of COVID-19 and I can talk of epidemics, but I won't be talking about machine learning and predictions at all. Are you sure you want me to come and give you a talk? And they said, yes. So here we are, okay? But you will not hear from me about machine learning and predictions because my field is different. So I will bring you my perspective as a mathematical modeler. So my background is in maths. And what I do is I want to understand the epidemiology and the dynamics of the epidemic. My research is very much based on data, so I'm trying to learn as much as possible from the data, which we know have many limitations. We need to be aware of the biases as well, as Laure said. And what is interesting to me is really we want to quantify effects. And for instance, we want to quantify what's the impact of a control strategy, for instance, and how we could potentially mitigate or control an epidemic. So you will see in the rest of the talk about, you will learn a bit more, I'm not sure how familiar you are, but about mechanistic and compartmental models. So we are not looking at associations with these models. We are looking for mechanisms of infection. What is driving the infection within a population? So we know how infections are passed from people to people, and we are modeling this exact process. In this sense, it's a mechanistic process. I will tell you a little bit about how we do model fitting. It's different from machine learning, but it's very much a rigorous approach, and it is a statistical inferential approach. It is well established. And instead of talking about predictions, looking at the future, I will talk to you about counterfactuals, which is looking backwards and asking the question, what would have happened if we had done things differently? Okay, so I'll talk mainly about 2 case studies. One is a paper that we published in Nature. It's about the suppression of SARS-CoV-2 in the Italian municipality of Vo, which is in the province of Padova. And then it's a follow-up article about a seroprevalence study in the same municipality. And I will have an additional slide on work in progress, just to tell you what I'm doing now. And so I started working on this first project on the 21st of February of 2020, essentially, because that's the day where the first COVID-19 death was found in Italy. And this death occurred in a person who was living in Vaud. He was an elderly person who didn't leave the village, you know, and this death was, I must say, quite surprising in a way, because we knew that there was an outbreak ongoing in Lombardy, but no one was aware of the extent of transmission of COVID-19 that was ongoing at the time. And what did we know as of the 21st of February? Well, I had been working for more or less a month on COVID-19, and what we had learned, this was work that we had done together with the Imperial College COVID-19 response team, was that the epidemic size in Wuhan was larger than it was reported. We had the first estimate of the reproduction number. That first estimate was around 2.5, so not too far from the actual estimates that we then observed, you know, by collecting more data. We had first few estimates of the case fatality ratio. So we knew that around 5%, this is from very early data, around 5% of cases, detected cases internationally, were dying. In terms of infection fatality ratio, it was a bit lower. And on the same date, on the 21st of February, we published our 6th report, where we were saying something along the lines, look, surveillance internationally is capturing around 30% of the cases, because we did that by comparing the number of flight data, the number of passengers data, you know, that essentially were leaving China and Wuhan at the time. We were comparing the number of predicted cases entering the countries with the number of cases that were actually reported. And we realized that this number was highly underestimated. And so we said that there could be quite likely the possibility of ongoing undetected, you know, transmissions that were ongoing silently in the population. And this is when the first COVID-19 death occurred in Italy, which was kind of confirming that this hypothesis was unfortunately a very real one. We had many questions, more questions than answers, of course. And these questions were, how many undetected cases are there? How fast is this virus spreading in the population? We had no idea. There was not much testing going on. When was the virus introduced? Are there symptomatic infections? If there are they infectious? Can they infect the others? And so many questions. So we tried to answer some of these questions with the studies that I'm going to present you. And so yeah, on the 21st of February, we had the first death in Vaud. And what the University of Padova and my colleagues there did, well, they went into this population, they went into this municipality, and they implemented what we call a mass testing screening strategy. So what they did, they received the approval to really go around in the village and start swabbing, taking you know, nasal and oronasal swabs of the people. And so we had information on the dates that the swabs were collected. These swabs were analyzed by PCR, so a molecular testing. That's different from the antigen testing that we are using more often now, but that's very high quality testing, the molecular one. And essentially we did what was the first SARS-CoV-2 prevalence study kind of ever done. We collected lots of information on the population. We collected information on the demographics, the age, the sex, the health conditions. We tried to collect information on the contacts. So whether, you know, people were in contact with other people who had been infected, on their symptoms. And so we tried to do a kind of a whole epidemiological analysis in this sense. And on the same date, on the 21st of February, Vaud went into lockdown. So we are in a context where in Europe, we were still discussing whether, you know, the kind of lockdowns that we had seen implemented in China were possible or not. So there was discussion. Some people thought that, you know, this kind of measures could never have implemented in the Western society. They would not have been acceptable and accepted. And actually, Vaud went into lockdown. And this was a strong, I think, a strong move in a way. And this lockdown lasted for 2 weeks. And what we did is, well, we did our first survey at the beginning of the lockdown. So we managed to swab the people of this municipality at the beginning of the lockdown. And then we went back towards the end of the lockdown to check what's the effect of the lockdown. So did the prevalence change within these 2 weeks where people were asked to isolate and to diminish their contacts, essentially? So what we found, well, in terms of study size, we managed to enroll 86% of the eligible population in the first survey. In the second one, 2 weeks after, we managed to enroll 71% of the eligible population. There were some differences in terms of surveyed and non-surveyed population. We didn't capture the old age groups for clear logistic problems, but between the first and the second survey, there were no statistically significant differences in the population, which means that we could draw significant conclusions from our analysis. And so what did we find in terms of prevalence? Well, in the first survey, we found a 2.6% prevalence in absolute terms. So in a village, in a municipality with little more than 3,000 inhabitants, we found a total of 73 infected and infectious people at the time of the swab. And yeah, just to put this into context, this is, again, remember that it was the very beginning of the epidemic and the pandemic in Italy. There was, it wasn't a known thing that the virus was spreading. So this was really kind of an eye-opening surveying in a way, because it demonstrated that what we had thought could be possible was actually happening on the ground. And so at the end, in the first survey, we found these 73 positive subjects. And at the end of the second survey, we found that actually the number of positives were much lower. They were 29. Many of these 29 were the people who were positive on the first one. And so in between the first two surveys, we only had 8 new cases. And perhaps the most important, or one of the most important findings of this study is that we were really able for the first time to quantify what is the proportion of people who are asymptomatic. And so across the two surveys, we estimated that around 42% of the people testing positive were completely asymptomatic, which means they were not symptomatic at the time of the test and did not develop symptoms afterwards. Because what we did is we followed the people. So we did not just, consider the symptoms occurring at the date of the test, but we followed people up to 3 weeks afterwards, and we asked them whether they developed any symptom at any point during the 3 weeks following the positive test. So in terms of symptoms, we found that, the most common symptom was fever and cough, but there was a range of different symptoms and actually combination of symptoms that were reported. So interestingly, at the beginning in this survey, we did not find any positive children between 0 and 10 years of age. And at the time it was, a very much debated result, because we had not much information in terms of, infections coming out of China. We didn't see any infection coming out from Vo. And people started suspecting about whether children are perhaps not as susceptible as adults to the infection. Well, now we know very well that actually children are susceptible to infection. It's probably just more a matter of the children are likely less symptomatic. So we were very aware and cautious about framing this result, I must say. What we found, likely due to the social context within the municipality, that actually the elderly population had 3-fold higher prevalence than the younger population. We didn't see any difference in terms of asymptomatic and symptomatic infection by age, but again, let's remember that we did not have data on the youngest age group, so between less than 10 years of age. We observed that most of the people, nearly 60% of the people who participated to both surveys, actually cleared the infection by the time of the second survey. And we found that infection was actually more frequently associated with an old age, and in the second survey with being of male sex, which is something that has been observed in the literature as well. The next obvious question for us, because we found that there was such an extent and frequency of asymptomatic infection, was what's the potential of asymptomatic infections to infect? Do they have the potential to infect? And so to answer these questions, we look at the viral load. And what we found is that actually looking at the viral load, remember, we just had a single, or when we were lucky, 2 point estimates of the viral load. But overall, looking at these estimates and this data that we had, we didn't find any significant difference in viral load between symptomatic and asymptomatic infections. So therefore suggesting that potentially asymptomatic infections could transmit this virus onward. Of course, there are symptoms, it's coughing, that could amplify this risk in symptomatic people, but at least from a potential perspective, the viral load was really not different between these 2 categories of people. And when we looked at we tried with the data that we had to look at the dynamics, or at the trends in the viral load in time. This is the panel that you see on the right. Well, you saw that the viral load really tended to peak around the day of symptom onset. And this was a clear suggestion that actually infectiousness and transmission of this virus must have been ongoing before the date of symptom onset, which from a public health perspective was a really challenging thing to address. We also had the evidence that there had been a few infections occurring in families, in households where there wasn't any symptoms from the infector. And clearly we estimated that, the living in close contact with infected people brought higher chances of being infected. We then looked at transmission chains. And so we tried to reconstruct it essentially who infected whom by merging the data that we had on the infection from the swab survey and from the contacts that were reported. And we did this, we reconstructed the transmission chains because we wanted to quantify 2 key epidemiological estimates. One is the serial interval. So the serial interval is the time from symptom onset of the infector to the symptom onset of the infectee. And so this is kind of an epidemiological relevant parameter because we need it essentially for modeling, for modeling purposes, but also because we need this parameter to estimate the reproduction number. So, and the reproduction, what is it? It is the average number of secondary infections generated by a typical infection in a fully susceptible population, okay? So it is the average number that one infected person at the beginning of an outbreak generates throughout their infectious period. And so we estimated the reproduction number from the transmission chains, because once that we could reconstruct who infected whom, it was kind of easy to count how many new infections each person caused, and therefore averaging that. But it's also important to estimate the reproduction number because we can estimate, it was also important to estimate the serial interval because we can estimate the reproduction with estimates of the serial interval at a population level. So what we do, and so in general, when you work at the population level and you have estimates of how the incidence is increasing, of how many new cases you have in the population in time, well, you see that, if you know how long the serial interval is, you can attribute the number of cases observed after that serial interval to the initial case. And in a sense, you can really reconstruct what the reproduction number is. So we did these sort of exercises. We reconstructed the transmission chains. We obtained estimates of the serial interval of 7.2 days, very much in line with estimates that were coming out from Lombardy at the time. And we found a reproduction number of 2.44 before the lockdown, which was completely crashed after the lockdown, like very much under the threshold of 1. We know that the reproduction number has this property that when it is above 1, then there is exponential growth and an epidemic occurs. When the reproduction number is below 1, well, we don't have an epidemic essentially. And then we did some transmission dynamics. So what do I mean by transmission dynamics? So the data we had coming out from VO were 2-point prevalences, okay? So 2 prevalence data at 2 different time points. One was at the first survey and one was at the second survey. We were able to stratify that by the infectious status of the people, whether they were asymptomatic, symptomatic, or pre-symptomatic. What we want to do with a dynamical model is we want to reconstruct the dynamics, that's the lines that you see in this figure. And so we want to capture, what's a process that has been ongoing in the population so that we can reproduce the prevalence estimates that we observed in the population. How do we do that? This is one of the basic models. It's called the SIR model, one of the most basic compartmental mechanistic models. And so I thought I would tell you a little bit about this modeling approach, which is not machine learning, but it's what a mathematical modeler in my field would often work with. And so what we do with this is we classify people according to their infectious status. So we say you're either susceptible or you are infected and infectious. And after you are infected and infectious, after some time, you're going to recover. And so we classify people, we put them into compartments according to their infectious status. And we assume that within these compartments, people are all the same. So we don't look at other heterogeneities, okay? That could be age, that could be behavior, many different things. So it's a very crude approach in a way, but this is mathematically tractable. And what we do is we try to assign rates. And we assign rates to these flows. So we say, okay, what's a rate? What's the chances that a susceptible person becomes infected and infectious? Well, then, so you can try to think about it from a personal perspective. So if you are a susceptible person, well, what are the chances that you catch the infection? Well, there are the chances that you go out and you infect and you contact someone who is infected and infectious. So the probability of meeting someone who is infected and infectious is 1 divided by n. And then the beta captures 2 different things. The number of contacts that you make. So the more contacts you make, the more chances you have to be infected. And the probability of infection upon a contact, okay? And so what we call beta I divided by n is what we call the force of infection. So that's kind of the pressure that each person, the per capita risk of infection, the pressure that each person feels on them, trying to infect them. And after you are infectious, you are infectious for some time, but then you recover. And so there is a rate of recovery, a daily rate of recovery, or if you want, after on average 1 divided by gamma days, you will feel better, you will have immunity. And so this is kind of just to tell you a little bit about the basis and of what one of the most fundamental models in epidemiology, which is the SIR model. So what we did in VO is, starting from this very simple model, well, we modified this model to be able to capture what we saw in the data. And as you can see in this figure, this is a modified version of an SIR model, but not too modified. But how did we have to modify it to capture the data? Well, we had to include an incubation period. That's what we call E. So people, when they get infected, they are not immediately infectious. There is a phase of incubation where the virus is within the body of a patient, of a person, but the viral load is not as high that they can immediately transmit it. So there is an incubation period. And then notice that because we had data on the pre-symptomatic phase, we wanted and we had to include a category which we call the test positive TP, where it is essentially the pre-symptomatic patients and infected people. We assumed that a proportion of these people were developing symptoms, the other people were completely asymptomatic throughout the course of the illness. And then to capture this data, we had to include 2 other categories where we were detecting, we were still classifying these infections as positive, but we were assuming that they were not infectious anymore. And this is perhaps one of the things that is completely accepted now, but it wasn't at the time. But now we know, in fact, that PCR tests are very, very sensitive and they can detect low levels of virus, likely after the infectious period has finished. But this model clearly, the structure of the model that we had to employ was telling all of these things essentially to us. How do we do model fitting in my field? Well, we do model fitting. Typically, we do that in the Bayesian framework. And the Bayesian framework, Bayesian inference, is very much based on Bayes' theorem, which tells us that the posterior distribution, the probability of the model given the data, is proportional to the likelihood, the probability of the data given the model, times the prior distribution, okay? And so with Bayesian inference, what we want to do is we want to determine the posterior distribution. Typically, we use MCMC. It is a method that allows us to sample from the posterior distribution. And it's particularly powerful because you can apply that even when the likelihood is not tractable. And this is just an example because I thought you might like it, to look at the Metropolis Hastings algorithm. So what do you do in practice when you do parameter estimation? Well, you must have a proposal distribution. So you start from one value of the parameter and you say, well, I modify it slightly. So this is a proposal distribution. And then you have a rule to tell you if you accept this new value or not. And so this rule is proportional. It depends on the ratio of the posterior probabilities. And also it depends on a correction factors, which depends on the proposal distribution. Okay, and so you accept a new value with a certain probability, and otherwise you reject it. Okay, and yeah, depending on the choice of your proposal distribution, where you can have different algorithms, and what comes out from these MCMC methods, this is an example, for instance, from one single parameter, is that you have a Markov chain of posterior values, okay? So this tells you that after some time, the model converges, and from this posterior sample, you can actually draw inference on what's the posterior distribution of the parameters. So you can calculate your statistics, the mean, the median, your confidence interval, and so on. This is what we did. So when we do model fitting, we apply these sort of algorithms. And so we parameterize the model. We found very reasonable estimates, I must say. So of course, we estimated a mean of 41% of asymptomatic infection that was matching what we were observing. We estimated an infectious period of 3.6 to 6.5 days. We tested different assumptions on the reproduction number. We estimated that infection was seeded in the village around the beginning of February. So we kind of made inference about when the virus was introduced. And we estimated that the lockdown clearly reduced transmission substantially, between 82 and 99%. And then we did some counterfactors. So this is an example of the counterfactors that I mentioned to you at the beginning. So with the lockdown, with our model, as was initially parameterized, we estimate that at the end of the wave, around 4.9% of the population would be infected, was infected. Well, then the reasoning was, what would have happened if the lockdown was not implemented, okay? So what would happen if we did not apply that reduction in the number of contacts, in the transmission rate that we had estimated? Well, in that case, we estimated that around 86% of the population would have been infected. So the lockdown really, that intervention was particularly successful and, in really suppressing this epidemic in this context. And so what did we conclude? Well, SARS-CoV-2 clearly had spread and was spreading silently in the population. We found that 42% of the infections were asymptomatic. We hypothesized that asymptomatic infections could contribute to the onward transmission. No infections in the children were found at the time, but that didn't mean that children could not get infected. And clearly, perhaps one of the main really results of the study is that it was, in a way, in itself, a demonstration that the SARS-CoV-2 outbreak could be suppressed. And to follow best practices, we made all the data and code available so that they were reproducible. And then I wanted to talk to you about the second case study, because we followed, this initial study, was followed on by other two serological and swab surveys. So what did we do? We went back into the same population, that was May 2020, and we went back to test for antibodies this time. So we wanted to look at what kind of immunity was left by this wave into the population. So this time we managed to recruit 2,600, around 2,600 people. That's 78% of the population of VO. And for the vast majority of them, this is the beauty of this data set, for 88.5% of these people who were, who were tested by serology, well, we knew what was their infectious status according to the PCR results that we had obtained in February and March. And what we did is we did not just use one assay to test for antibodies, but we were interested in comparing what the results were in terms of exposure if we were using 3 different assays. And these were the 3 different assays that were most commonly adopted around the world at the time for seroprevalence studies. So we looked at the Abbott. It's a test that tests for the N antigen, the diazorin, it looks for the spike, and the Roche, again, for the N antigen, but it's a total antibody test, not just IgG antibody test. And we also did the neutralization one. And so what did we find? So because we wanted to test the same samples with different assays, well, then we had to deal with the issue of assay discordance. Because, one sample, for the majority of the cases, one sample testing positive with one test will test positive also for another test, but that's not always the case. So one sample could test positive with one test, but test negative with another one. And we saw this issue coming up. And so this discordance in the assay at the individual level, well, was an issue because it gave us different population level estimates of the seroprevalence in the population. And this problem was actually even higher when we tried to correct for the sensitivity and the specificity of the assay adopted according to the validation studies that were done in the lab that processed these samples. And so what we did really, the question is, what is a true seroprevalence? Can we use all the information that is contained, by using these 3 assays and find what is a true value of the seroprevalence? And so we answered this question with a statistical model. It is a likelihood-based estimate. When we tried to really combine the estimates that we saw coming out from the seroprevalence studies in terms of what's the result of the different combinations of the assays, and what is the sensitivity and specificity that we saw coming out from the validation experiments in the lab. And then we compared our estimates, this 3.5%, that is a yellow line in this figure, with another definition that we tried to make, which actually captured the estimate appropriately. And basically this ground truth definition was a definition that included having tested positive by PCR and being positive by a serological assay against at least 2 different assays, so one N and one S assay. We look at the associations. So we looked at whether the antibody levels and the decay in the antibody were different in the population by demographics. What we found is that there were differences by age and by BMI categories. Specifically, we saw higher antibody titers in people with higher BMI across all the serological assays used. But we didn't see any difference really in terms of, antibody titers and decay rate by symptomatic or asymptomatic infections, by severity, hospitalized and non-hospitalized patients, and males versus females. We looked at the antibody decay because remember we went back after May, we tested the same people, or most of the same people in November. And essentially we looked at whether the people who tested positive in May were still positive in November. And what we realized this time is that actually the answer to this question very much depended on the assay that you used. So for the Abbott, only 36% on average of the people testing positive in May was still positive in November. For the other two assays, it was much more. So for the diazorin, it was 78, and for the Roche, it was 98%. And then we had found evidence that some people must have been or were likely re-exposures, because we saw the antibody levels really increasing between May and November. And most of these people really reported contacts either with PCR positive people, or they reported having attended large events where potentially exposure could have happened. But the good news was at the time that really these potential reinfections and or these re-exposures did not really experience any symptoms. So in a way, the pre-infection was kind of lowering the risk of symptomatic infection. And then we did some more modeling. And this time we did some modeling. We wanted to better understand what was the probability of transmission of SARS-CoV-2 within the household setting. And so to answer this question, well, what these several prevalence surveys told us was really the true serological status, whether people were infected or not within households. And so we knew what, the proportion, what the attack rates were in the households, and we knew the household sizes of these households. So we kind of knew what was the proportion of households of size 1, 2, 3, 4, etc., that were infected. And so we really wanted to capture these proportions. Again, we used what is called the chain binomial models, and this is an example of it. Essentially, what we do with these chain binomial models is, well, we assume that there is a fixed probability of transmission between people who live in the same households. And we say, okay, so if we assume that there is a single introduction in a household of size 3, well, what's the probability that at the end I have 0, 1, or 2 cases infected? And so essentially, we estimated this probability that households of size n with an initial number of susceptible had so many infections. And what we did was we tested many different assumptions. So we wanted to test what are the assumptions that allow us to best capture the data, okay? And so we tested many different assumptions. One was there is over-dispersion in the number of secondary cases. That is to say, the reproduction number is not constant. There is large variability in the number that one infection causes. Another assumption was, well, there is household size dependency in transmission. So for instance, you can imagine households with larger households may have a higher or a lower risk of transmission within the households as compared to smaller households. We assumed whether there was seroreversion. So people who have been infected and testing positive by antibodies, well, if they were testing negative after some point. And we included the hypothesis that there was a proportion of subjects in the community that were completely excluded because they were self-isolated. And what we did is, well, we used goodness of fit and a model selection criterion. It's called the DIC. We looked at the very different models. What came out very strikingly is that the best models, what really allowed us to better capture the data, is that we needed this assumption of over-dispersion in the oxygen distribution, which means that really the R0, the reproduction number, is not fixed, not even in this population that is relatively small. So we saw that there was really high heterogeneity in the number of secondary cases that an infection was producing. And we estimated that 82% of the transmission was really due to 20% of the infections. We also estimated, this was one of the first estimates of what we call the SITP, the probability of transmission between susceptible infectious pairs within households. And we found an estimate of around 27%. And then we did another counterfactual analysis because we could leverage our knowledge, and the data that we had from the surveys info with the contact tracing data. And this time we used not the data that we collected from our own contact tracing, but we used the official contact tracing that was done by the public health authorities at the time. And this is in a context where really at the beginning of the pandemic in Italy, there was a huge effort in trying to identify patient zero. And so what we found is that, well, 30% of the traced contacts were positive because we managed to estimate these two things by, kind of intersecting the results of our mass surveys with the results of contact tracing. And we knew that 44% of the PCR positive subjects were traced. And so then the obvious question for us, was what would have happened? Well, if, contact tracing was not conducted, but most importantly, if mass testing was not conducted. So we modified the model that you saw before to allow to include contact tracing. And really what we found from these analyses was that contact tracing had a limited impact on the epidemic. And what was key really to control this epidemic was more the mass testing, or in other words, the isolation of the infected people. And really what we found from this work is that really the seroprevalence estimates did vary by the assay used. And in this sense, we really cautioned for really trying to understand the data in the context where they are created, like, and cautioning people from comparing seroprevalence estimates obtained in one place of the world with another place of the world, with different assays and, for instance, with different timings from the epidemic. It was quite clear, and there was a clear indication that antibody decay really varied depending on the assay used. Well, first there was an indication that antibody decay, and okay, but then this decay varies by the assay that you use. And it became clear that the Abbott assay really suffered of this decay more than the other assays. The Abbott assay was the assay that was used in Italy for the National Seroprevalence Survey, and we really don't know, it is possible, but it's hard to judge whether, the estimates that we obtained from that National Seroprevalence Survey suffered a bit from this problem. We had, evidence that at least up to 9 months post-infection, the antibodies were persisting. We didn't see difference by severity. We did see some difference by age. And yes, from the modeling work, we saw that most of the transmission was really due to the minority of infections, which was important to really stress how the behavior of everyone is important. So behavior and adherence to recommendations is important, because we saw that it was actually the minority of the infections that were causing the majority of disease in the population. And therefore, we really advocated for an enhanced surveillance, also including for, contact tracing, for instance, by digital contact tracing, or, other forms of surveillance, even, in the presence of vaccine rollout. In terms of work in progress, well, I'm now looking at a multi-strain model. We are now working on this new model where we are looking at what's the effect of different testing strategies on the dynamics of different variants. And this is in the context of a study. This was initially, this started as a surveillance study conducted in the hospital in Padova, where they were simply testing, patients both with an antigen test and a molecular test for diagnostics, purposes, not really for diagnostic purposes, but just for to confirm, the validity of the antigen tests. And what came out of the study is that actually there was one variant which wasn't particularly virulent, but there was one variant that was escaping the antigen tests, essentially. So it was one variant that was rarely, if never, detected by antigen tests, by the rapid test, but was actually detected with the PCR tests. And so in this sense, we are doing this work to better understand what is the role of molecular testing. So should we do molecular testing after a positive antigen test, after a negative antigen test, and what is the impact of the antigen testing strategy, of the testing strategy that we use? And what would happen if we only rely on antigen testing and we do very few and very little confirmatory molecular tests? I have a couple of slides on the concept that projections, which is what we do in mathematical modeling, is very different from predictions. And I thought that this would be a very useful platform to do this distinction, because the title of the session included prediction, and I guess this is what machine learning often wants to do. You want to predict the outcome, you want to predict the future, and maybe in this context you may think, well, you want to predict what happens tomorrow. But as I said, and as you have seen, I haven't even attempted to predict what happens tomorrow. I only look backwards and I did counterfactuals so far. But what we do often, so we do projections, which is not predictions. And so what are projections? So projections, you can think of projections as scenario-based modeling. So essentially what we do is we have a model to really look at how the epidemic can spread into a population. And what we do, we are often asked for the government or for policy purposes, we're often asked to explore scenarios. And these scenarios really tell us about hypotheses of how the virus may change, or how the new variant, how transmissible is new variant, how severe is new variant, what the potential impact of an intervention could be. And what we do is we take this hypothesis. We don't know if these hypotheses are right or not. No one knows. And we simply simulate this hypothesis, and we do projections of the impact of this hypothesis on the epidemic dynamics. And often we look at, for instance, hospitalization rates, because now we know that the interest is in, keeping the hospitalizations perhaps under, a certain limit. And really what mathematical modeling helps you do is it helps you really, let's say it in the words of Robert May. Robert May is one of the founders of, mathematical modeling for epidemiology. It forces clarity and it forces precision, okay? And so it allows you to do meaningful comparisons between the consequence of your assumptions and what you see coming out of the model and the empirical facts. And if I want to be a bit more cynical in a way, but in other words, modeling is a better option than just relying on the gut feeling, common sense, or plain old wishful thinking that would replace it. And this is in the words of Keith Yates, who published this nice column yesterday in The Guardian, if you're interested. And so I think, yes, I just wanted to clarify that, projections is a very different thing from predictions. When we do projections, we do not know which of the assumptions, which hypotheses come true, but we can see what the consequences of each hypothesis would have on the epidemic. And just to tell you a little bit about how the modeling works in conjunction with policy, well, government typically contact academic groups. This is specifically in the UK, in Italy is different, but and government typically communicates potential strategies, potential policies to modeling groups. Modeling really try and model these policies, and they report back to government about the findings. And the government takes decisions according to the finding of this modeling work, combined with many other different considerations that go beyond the public health aspects. I consider economics and policy and politics and everything else. But critically, there are uncertainties in the projections that we produce, and different groups will bring different results. It's a natural thing because different groups will do different modeling assumptions, and different groups will have different uncertainties. And actually there are intrinsic uncertainties in what government typically asks us to model. For instance, if we have a new variant, there is lots of uncertainty around the transmissibility of this new variant. And so we will have to model uncertainty around the transmissibility, whether there is vaccine escape or not. What's the severity of the new variant? These are all things that are impossible, I would say, to know very early on. You can make assumptions on it, but really, unless you have observed the data and you have the evidence to estimate that, you can't know these things in advance. You also have uncertainties in terms of interventions because people's behavior is unpredictable. How people are going to accept some interventions and not others, it's a really hard thing to know in advance. You know it after you've done it, but you don't know it before. Upper limits are important in this sense because often the government wants to avoid the worst outcome. And so in this sense, it's important to communicate that, you know, your results are not fixed. You give a mean, but you have a confidence interval, and the limits of this confidence interval is important. And because the modeling is, you know, used for informing policy, well, I think there has to be an understanding that the results obtained from these projections that are used really cannot match. If they work, if these projections really work and they do their job of advising policy, well, it will be very unfair, and it's not the right thing to compare the outcome of these projections with what really happened in reality, because it is the purpose of these projections that often is to change the policy and make sure that the worst outcome do not happen. And so in this case, you know, this is something that actually we have observed sometime, you know, in the media for whatever reason, but it really often does not make sense to really go and compare what's the outcome of some projections, perhaps even worst case scenarios, you know, with what has happened in reality with different conditions compared to what the models, you know, had implemented. And this is my last slide. I want to thank you for your attention. This is my email address. Feel free to contact me if you're interested in this field, or if you would like to discuss any of the work that I have told you about today.
Thank you, Ilaria, for your fascinating talk. And we are a bit late, but happy because all the talks were really amazing. And if you agree, we can just take a round of the burning question. I start with Ilaria, since she has just and now, and I take a cue from your last slide, because I was remembering I remember an editorial to The Guardian which was written by Spiegelater and Sylvia Richardson about these two kind of culture of modeling: the empirical modeling, which is based on fitting curves on the data, and the modeling of epidemics. And what we have seen in this month about COVID data is a lot of different types of modeling, and also a lot of machine learning. And promises of machine learning was just to fit black box with a lot of kind of data. So not just data relating to the transmission, but also, for example, air pollution and meteorological data and mobility data and so on. What is your opinion? I mean, I think that public health decision taken by policymakers was mostly based on epidemic models like yours. But do you think about, I mean, the other kind of modeling? It has a future in this field. It could be adopted along with more traditional.
Yeah, so I think, yeah, this is a very good question, I must say. So, you know, I think in terms of policy, if you want to implement, say, and if you want to kind of try to reproduce what the potential impact of interventions is, well, you need to have a mechanistic model in this sense, because you need to be able to act, you know, on what the mechanism of the transmission is. And so I think that very much, you know, in terms of informing policy, in terms of what's the impact of interventions, there is a value in this kind of traditional mathematical modeling. I agree that it's an interesting idea to look at, for instance, you know, what's the role of pollution? And I've actually worked a little bit on this as well. Not really on pollution, but just looking, for instance, at the role of temperature. Like, is temperature really driving the virus transmission, or are there, you know, other factors? And I think we need to be very aware that there are lots of biases in this. So I can really just echo what Laura was saying before, because yes, we can feed into these machine learning models lots of different things, but we always need to be careful about what are we really measuring. And I'm saying this because, for instance, pollution. You know, early on, there were lots of talks, and I was involved in meetings where people were really convinced that pollution was a driver. And, you know, there were physical explanations of how pollution could drive this virus further away. But then there is this problem that pollution is, you know, very much linked to the geography, if you want, of a place, and to the number of people who live on a place. And this is a virus that thrives when there is large number of people, you know, living in the same place. And so very much there was, I think, a bit of, you know, there is high correlation between, for instance, you know, population density, the fact that you live in an urban as compared to a rural setting, air pollution. So how do you disentangle whether the effect that you see is due to pollution as compared to, you know, population density? So yes, I believe it's a very useful thing to explore, but let's always be careful with potential biases, and let's always try to understand what are the real drivers of transmission as compared to, you know, just casual maybe or random associations, which have maybe something else to do, you know, and then they're not really the driving forces of the epidemic.
Yes, in the last days, we had a talk about with a PhD student of Mark van der Laan, who is working on causal inference for machine learning, and maybe he could have a clue about that. I mean, a potential way to explore some these things. Just a curiosity. In your Bayesian model, which kind of prior did you use? I mean, did you use informative or weekly prior?
I don't remember off the top of my head, so I would need to go back and check. But usually, yes, it's always useful if you have informative prior, at least even if weekly informative prior, you know, to use them. Actually, I think that we used uninformative prior, but with bounds, you know, not completely wild in a way. But yeah, different models, you know, will work differently. Yeah. So sometimes it may be possible, especially when you have a very complex model, by experience, you may need to inform the model, at least partially, with your prior. But as long as, you know, you're not forcing the model and you're not receiving as an out, you know, as long as your posterior is not the same as the prior. And so as long as you are conducting inference for real and you are checking, there are several checks, you know, and that you can do to estimate, you know, and to check whether the inferential framework is working and is reliable if you have correlation between the parameters, you know, and how to deal with that. Usually, you know, these methods are robust and they have been used for quite a while, I must say, in the field.
Thank you very much. I was checking, but okay, I think that we can move on the question for Laure. And if some of the panelists want to ask something to Ilaria, or they want to make some comments, they are welcome, they are free.
No, just thank you. I really like the presentation. No.
Likewise, eh? And maybe, yeah, just Paola, just let me clarify that, you know, I think, yes, machine learning is absolutely something worth exploring. It just to clarify my previous comment, but yeah, let's be careful about the conclusions, but definitely it's a powerful tool that allows to explore relationships that are very high and very difficult to capture otherwise, in a way. So let's put it in this way. So definitely, and yeah, just to go back with Laure, I'm also looking at primary care data, trying to use machine learning to learn about the outcome. And this is in the context of dengue. So it would be very great to talk maybe.
I would love that.
I would just discuss about your conclusion about sharing the models, I think, which is a common question for everyone. And I think there is a hot topic about moving from models to decisions, which is, I mean, there are also many European call about this topic. And I mean, I appreciate the Laure conclusions about sharing the model, and maybe the models are our new data in the futures. And maybe instead of relying just on one model, I mean, we should stick on ensemble of models. And what do you think about this?
Yeah, there's actually two responses to that, I think. Well, of course, if you have ensembles of models, you are less influenced by, you introduce some uncertainty, or you take into account the uncertainty or the biases some particular models will have, and you average that out. So on average, your predictions are going to be a bit better. But it becomes problematic if the underlying models are all biased, or the majority of them are all biased. So yes, definitely a good idea, but not without checks on the quality of the models that are the input, I think. I don't know if that's a complete answer to your question. It's a short one.
No,
Yeah.
I mean, yeah, we have an uncertainty within the model and uncertainty between the models, across the models. So it's complex. But I think there are many, I think in epidemic is quite usual to evaluate an ensemble of model.
So it depends on the type of modeling that you do. So typically when, we do this type of compartmental modeling, each one develops their own model, and that's what you present. But for instance, when we try, and so there is a different type of modeling where we estimate, for instance, the reproduction number in time. I guess everyone has seen one of these, right? Where we see the number of cases and you apply a method and, you estimate what your reproduction number is, and then you project forward. You say, okay, if conditions stay the same for next week, then we predict this number of cases. And these estimates, sometimes they depend, different methods will give you different estimates. And they are all epidemiologic from an epidemiological perspective. They are all valid, but they give you slightly different estimates. And I've seen this averaging being done. So, they take these projections forward and they average them. And I think it's quite fair to do this, to be honest. In this context, I think it's totally fine. As long as, there is not wild inconsistencies. I think it could be a way of accounting for, different assumptions.
The poor quality of research, which has been published, has sparked a lot of questions for Laure. And in your opinion, why these poor results have been published? I mean, poor reviewers on something else. Would you have some clue about that?
Yeah, I think in a way it was a perfect storm of a cross-section of two very hot topics. On the one hand, AI in health, and on the other hand, COVID, which may have made editors more lenient to accept these papers. On the other hand, there was definitely the time pressure. I remember getting so many peer review requests, and there was such a hunger for information at that time that I can definitely understand that, editors are trying to speed up the process, and I've seen that happen. So everyone will have had these review requests, requesting a review within a couple of days because they wanted to make it a quick process and publish these results very soon. So that cannot have helped. But more in general, I think there is an issue with peer review of prediction models, especially in the clinical journals. I think if there's not statistical peer review, many of the issues aren't recognized. And even people who have a basic knowledge, they can do in their head a sort of checklist, like bootstrap, yes, that's good, cross-validation, yes, that's good, but more subtle ways of leaking outcome labels, for example, between the train and the test set, they will not capture that. So I think there is a problem with the whether or not the peer reviewers are capable of doing this review. But also another thing that we noticed, because we had the preprints that we included, after they were published, we assessed them again and included them again, because we knew, well, we expected, we hoped, if the peer reviewers pick up these problems or if the authors read our comments, they may make improvements, especially because we pointed out that a lot of the problems were in the statistical analysis and not necessarily the underlying data. So they are fixable. And what we see is that very often that didn't happen. So it was published in a very similar form with the very similar problems, and the authors were either not responsive to our feedback or the peer reviewer feedback, or the peer reviewers didn't pick up these problems. I don't know which of the two it was, but yeah, there must be a problem with the peer review process as well.
And also, why, in your opinion, calibration assessment of the model is so overlooked?
Yeah, I think that has to do with our tendency as humans to favor binary thinking. So we like to think in black and white or yes and no, and we forget there's 50 shades of gray in between. We tend to forget that if we classify, the uncertainty comes out anyway. It becomes misclassification, and it affects your sensitivity and your specificity. So there's often the belief that doctors favor a clear yes and no answer. And that's often used as an argument to only look at classification and classifiers rather than giving the underlying risk prediction models and the underlying risk spectrum. And I think that explains in part why people don't look at calibration. I think the other part is that, which I need to nuance, because I think for clinical decision-making as well, this risk is very important. I mean, it makes no sense to hide the uncertainty, because I mean, if you would group people from 0 to 50% risk and 50 to 100% risk, first of all, that 50% threshold is completely arbitrary and in many cases widely inappropriate. But also, you would treat a person with 51% risk and 49% risk as completely different, which makes no sense. So if you would show the actual risks to a doctor, that would influence how they interact with this model. The second point, the second reason that I think is often not presented is that calibration is just hard. It's just difficult to get your calibration right. And I'm not even convinced that you can get calibration right, that you can have a universally calibrated model. What I see over and over again is that even the models that are made very well and work very well in their setting don't transport to other settings. So if you do a validation, it's very disappointing often to see the calibration results. On average, it may work, but there are big differences, which are mostly related to differences in patient spectra, I think, or the way that care is organized. But that may also be an explanation. It's just a lot harder to get the calibration right than to get the discrimination or the ROC curve right. So yeah, hope that's an answer.
And maybe several models wouldn't be published if they look at that calibration. And some comments about that. I don't know if Liana or Danila wants to come to the discussion.
I have just a small comment, and thank you very much, Ilaria and Laure, for your very insightful presentations. Were very interesting. Well, I read recently a paper published on BMC, and calibration was defined as the Achilles heels of model development, and probably because these models are not truly intended to be used in clinical practice, because for clinical decision making, it's absolutely important to have a good idea of the risk, of the probability of a given event. And so miscalibrated precision is clearly harmful for clinical decision making. And so the point is, probably we are developing too many models without trust in them, probably because they are not truly intended to be applied in the real world to assist clinicians. So maybe could be the point. And as Professor Frank Harris said, probably external validation is overrated. And on the other side, calibration received too less attention that it should be. That's my point.
No, that's a very that's a very nice paper that you're referring to, and I agree well with the message of that paper. Yeah, I think I'm not completely convinced that the message in the paper though was that external validation is overrated. I think you have to look at it, especially if you want to transport a model, but one external validation or just a few external validations are no guarantee that it will work in a third data set or a fourth data set. In that sense, yes, well, the amount of information that one external validation gives you is very limited. But if you see that a model is reasonably robust across a whole wide array of settings, well, that of course gives some more confidence as well.
So you have also shown us that maybe logistic regression is still the killing application in analysis of clinical data, and maybe machine learning is too much because we don't have so huge sample size. But for example, how about using machine learning to help in automation of systematic review, for example, for screening abstracts and so on? I would like to leave on a high note about machine learning.
We actually used some machine learning in our screening process. After the first round, I don't know if it was after the first or after the second, but at one point it just wasn't possible anymore to do all the screening by hand. And we used some machine learning, which worked with word triads. I don't remember the specifics or the ins and outs. It was our librarian who recommended this approach. We set I do remember we set the threshold very low because we didn't want to miss anything. So also there you can tweak how sensitive you want to be. Well, it's very promising too, and it can take some of the hard and more boring parts of systematic review out of your hands. So yeah, that's a promising promising path that I do look forward to.
So we can say that machine learning is a promising tool.
I mean, I guess that I completely agree with you. I mean, given the amount of papers that have been published, which are completely unmanageable by a human being, right? And yeah, so these are kind of easy rules that a machine learning algorithm can be very useful, right?
I think we are a bit late, so I don't want to ask you to stay for much more time. And I really thank you all for accepting our invitation and for giving us really amazing and fascinating talks. So we hope we could have you in
other edition of this winter school next month.
In the
next year.
future.
Thank you.
Yeah, and thank you very much.
Thank you.
Ilaria and Laure and Danila, also Veronica.
Thank you for having me.
Thank you all for the invitation as well. Yeah.
Thank you, everyone.
Bye.
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 Thank you.
Bye. Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye.
Bye.
Bye, thank you.